Hey everyone, over the past year, I have tested more than 6 compact SLAM LiDAR scanners built on the LiVox 360 sensor. One issue they all share is drifting error during large scans, especially when covering area over 3,000 square meters in a single session. At that scale, the data becomes unreliable and can't really be used for building modeling. For example, in this 10,000 square meter 6th floor parking structure, every pocket-sized LiDAR scanner failed to complete the scan in a single session. The columns end up misaligned and the floors didn't line up with each other. The main issue is that the trajectory ends up being too long for the IMU sensor to handle. Right now, the LiGrip O2 is the only LiDAR scanner I have tested that can handle a 10,000 square meter 6th floor building without showing any detectable drifting errors. The LiGrip O2 uses IMU sensors that are over 3 times more precise than the built-in IMU found in the LiVox 360 that are widely used among the compact-sized LiDAR scanner. The downside is that this scanner's price is simply too high for a lot of users. So, with pocket-sized scanner, the only way to tackle large areas or multi-floor buildings is to break the job into multiple sections. That way, each scan stays small enough to avoid excessive errors, and you can align them afterward. In this video, I will show you how to align multiple scan datasets using CloudCompare. Let's kick things off with 3D scanning. The pocket-sized scanners I have tested, like the Chair C1, S20, Pocket 2, and Trion P2 can scan a 3-floor house in a single pass, but in this demo, I'll show you how to scan it floor by floor using the Manifold Tech Pocket 2. I'll be making 3 separate scans, starting with the first floor. With any scanner, during initialization, you need to place it on a level ground and make sure it's facing a feature. There are some scanners that actually move on their own during initialization, which is pretty unusual. When you break the job into smaller scans, the loops are shorter and less complex, and most scanners will give you more accurate results that way. Now I'm heading up to the second floor to scan the overlap area. This section will serve as the reference point for aligning the next scan. This small overlap area is more than enough for alignment with plenty of features like walls. You don't need to rely on checkerboards. This approach is both easier and more precise for interior scanning. Now I'm looping back to the starting point. Since this loop is very small, the accuracy will be higher. Now I'm moving up to the second floor to begin the next scan, and I have chosen this spot to initialize the scan. Now I'm walking past the overlap area I scanned earlier. Imagine scanning 2,000 square meters on a single hotel floor. Walking in and out of room after room makes the trajectory extremely complex. By breaking the scan into smaller sections, you will greatly increase the success rate. The key is knowing when to split the scan. I recommend using 3,000 square meters as the breaking point. Now I'm scanning the overlap area on the third floor. And now I'm closing the loop at the same spot where I started. Some scanners mark the starting point, which makes closing the loop easier, but with the Pocket 2, that feature isn't shown here. Now I'm moving up to the third floor, and I have chosen this spot to initialize the scan. So if your scanner has a fast startup time, running multiple scans won't be an issue. Now I'm closing the final loop. Many LiDAR scanners include a feature that lets you stop and continue the scan as a new project, then automatically align and merge the data. Manifold Tech calls this multi-flight stitching, FJD calls it continuous scan, and Green Valley refers to it as breaking point scan. With this approach, the software still treats the broken scan as a single slam loop. I have tested this feature across all manufacturers, and it consistently introduces more error. The only reliable way to eliminate drifting is to break the scan into smaller loops and align them manually. Now I'm running batch processing. Each scan will be calculated separately with its own loop. Here are the results of the 3 process scans. The origin point is set where you initialize the scan, and at that stage, the X and Y axis along with the floor level are also defined. I will export all 3 scans into LAS format, and then we will perform the alignment in CloudCompare. Please note the purpose of this method is to align the scan data precisely for CAD modeling. The aligned scans cannot be used to generate a 3D GIS. This tutorial is paced slowly so you can follow along. I will include the point cloud download link in the description. There are 3 separate floors available for download. This is CloudCompare. Go to Display and Display Settings and set the decimate cloud limit to a value higher than the number of points in the cloud you are viewing. I have set mine to 400 million points. This setting allows you to orbit the viewport more smoothly. In the Color tab, I will set my background to black. Now our interfaces should look the same. I drop in the first floor scan data. Press the F3 key to toggle between perspective and orthographic view. I'll be using orthographic view all the time. Click on the point cloud in the browser, then choose the Translate tool and set the Z-axis for rotation. Use the left mouse click to align one side of the wall with the edge of the window. Click on the Segment command, then use the Rectangular tool to select the required area. And next, choose Segment In and press the Delete key. Next, I will level the floor to the XY plane. Click on the point cloud, then choose the 3 points level tool. The 3 points I will pick are on the underside of the floor. After alignment, the building will appear upside down. After alignment, you need to rotate along the Z-axis again. From the Tool tab, click on Registration, then move the bounding box to the origin. And now the center of the first floor bounding box is positioned at the origin point. The building is still upside down, pointing toward the negative z-axis, so I will rotate it along the x-axis by 180 degrees to flip it upright. Next, I will use the segment command to remove the unnecessary overlap area. Notice that this time I'm using the segment out option. Next, I will use the segment 2 to remove the ceiling. It's blocking the floor visibility, and I need a clear view of the floor and walls for alignment. Next, select the point cloud and click on Save Current Entity. I will overwrite the original file to save the storage space. Next, I will drop in the second floor scan data. Click on the top view, select the point cloud, then open the segment 2. Use segment in to select the required area and press the delete key. From the Tool tab, click on Registration, then move the bounding box to the origin. Next, I will use the Translate tool to rotate the second floor and align the scan data to the same orientation as the first floor. Next, I will use the Pick 3 Points tool to level the second floor to the XY plane. After the floor is aligned, I will use the Translate tool to rotate and align the longer side of the wall with the x-axis. Next, I will flip the second floor along the x-axis by 180 degrees so it stands in the correct upright direction. Next, I will disable the X and Y translation and move the second floor upward. I will turn off the first floor visibility by clicking the check mark in front. Now I will work on the second floor. I will use the segment tool to remove the unnecessary overlap area. Select the point cloud, then select the segment out, then the delete key. I will also delete this one because I don't need it. Next, I will remove the ceiling of the overlap area to expose the floor and the walls. Now let's turn back the first floor visibility. To align the second floor with the first, I will segment and hide the upper part of the second floor scanned. The ceiling blocks the view, so removing it makes alignment easier. You can use either the segment in or segment out option, then click the check mark. Each segment will be separated into a different entity, allowing you to toggle visibility as needed. Now select both segments of the second floor and use the Translate tool to move them along the y-axis. When you toggle on the upper part of the second floor, you will see that both segments move together. In CloudCompare, hold the Control key to select multiple segments. This lets you move or rotate them together even while their visibility is turned off. CloudCompare has an alignment tool that lets you pair 4 points to align scans. I don't recommend this method. The accuracy is low, you will lose floor level alignment, and any hidden segment will toggle back on, blocking your view when selecting the points. Instead, I will use the Translate tool, holding Control key. I will select both segments while the upper part's visibility is toggled off. Then I will right-click to translate the scan data and align the floor level so it matches the first scan. I use my mouse to move it first because I will do the fine detail adjustment later. The lower part of the first scan is distracting, so I will segment this area and toggle off its visibility. Now with only the overlap area visible, alignment becomes much easier. On the top view, I will use the Translate tool to move the second floor scan toward the first floor. I'll click on the check mark first. When zooming in, you will notice the wall lines don't match. I fine-tune the alignment using the Translate tool with the rotation value set to 0. I will translate along the x-axis while disabling Y and Z translation. In the translation box, I will set the increment to 0.01 meter or 1 centimeter. Since the point cloud is very thin, I will reduce the translation increment to 5 mm. Click on forward or backward to move the scan data, then click the check mark when you are finished. Now let's adjust along the y-axis. I will use this wall line as the reference. I will enable translation in the y direction and use the forward and backward buttons to experiment with the adjustment. Back in the front view, I will enable Z translation and adjust the level alignment. You can see that the Pocket Tool scan is clean and produces thin wall lines, which makes alignment much easier. Adjusting at 5 mm increments makes the scan data merge seamlessly. Because I use the 3-point alignment tool to level both floors with the XY plane and rely only on translation for alignment, the floors remain perfectly parallel. If you know how to align your scan data properly, you can unlock more value from a compact LiDAR scanner. Okay, next I will talk on the visibility of only the upper portion of the second floor. Then I drop in the third floor scan data. Then I will use the segment tool to crop the required data and delete the rest. Next, I will rotate along the z-axis to orient the third floor in the same direction as the second floor. Next, I will use the 3-point alignment tool to level the bottom side of the floor with the XY plane. Keep in mind, selecting points from the underside will cause the scan data to flip upside down. Before flipping it back, I will adjust the orientation along the x-axis first. Now I will flip it along the x-axis by 180 degrees. Next, I move the bounding box to the origin. Now I will enable Z translation and move the floor upward. I will segment the third floor scan data, hiding the upper portion to expose the wall lines. Hold the Control key and select both segments, then click Translation. This will define the floor line of the overlap area. Use the Translation tool and right-click to drag the third floor scan toward the second floor. Back in the top view, I will use the Translation tool to drag the third floor scan data and roughly align it with the second floor. Let's move on to the fine adjustment. Set rotation to 0 and the incremental step to 5 mm. Then I will experiment with the forward or backward buttons. Now moving to the front view, I will use the Translation tool to make detailed adjustments along the z-axis. With the alignment complete, I will toggle on all the segments. By checking with the cross-section, you will see that this approach creates a perfectly seamless alignment for LiDAR scan data. Aligning scan data is time consuming. It takes at least 5 minutes to align a pair of scans, so it's best to break the scan area into a proper size, not too large, which can cause drifting errors, and not too small, which forces you to stitch too many scans together. With a 5mm incremental steps, the welding seam line becomes virtually invisible. You can't verify this by using cross-section command to inspect the alignment. We have segmented each scan into 2 portions. Now it's time to weld them back together using the merge command. Hold the Ctrl key, select the segments you want to merge, and then execute the merge command. When asked if you want to create a scalar field, simply choose No. Next, click on each scan and select Save Entity. You can overwrite the original file to save storage space. Each file will reopen in the same position, or you can weld all 3 scans together and save them as a single file. When importing point clouds into BricsCAD, you can place each floor on a separate layer. This is especially useful with large scan datasets, since you can toggle visibility part by part to reduce hardware load. Even though this approach completely removes floor-to-floor level misalignment, while orthogonality and parallelism still depends on the performance of your LiDAR scanner. With the Pocket 2, you will still notice about 1 cm of wall misalignment. To compensate, you should round off the right angle and wall thickness dimension by 1 cm. If you want zero error, the scans must be done with the LiGrip O2, but as I mentioned earlier, not everyone can afford this scanner. To get the full potential out of the budget pocket LiDAR, you need to break the scan into manageable portions and carefully align them as I shown you in this video. Some rotational drift still remains, but it's small enough to be negligible in most cases. Thanks you guys for watching. I'll see you in the next video.